In today's video, we're going to be talking about applications of circular motion. After watching this video, you should be able to use and apply some of the circular motion formulas that were discussed in Lesson 3 to a variety of real-life situations that deal with circular motion. So kind of answering this question of like, when would I use this type of thing? So let's get right to it. Race car tracks basically are areas where cars will drive around in a circle over and over again, right? So just to kind of start you off thinking about things, I'd like you guys to draw a free body diagram on this car, okay? And here's the track in which it's going around. And so what forces are present on this car? Well, as long as this car is on Earth, we're going to have the force of gravity, right? And that's going to always point down. We have a normal force, which is going to point up. Right? It's going to balance the force of gravity. And then there's a third force. The force that allows this car to actually stay in circular motion, to keep going in a circle, is the frictional force, the force of friction. And that's always going to point towards the center. You could, in theory, call that the centripetal force. But again, there really is no such thing as a centripetal force. It's kind of just a name we give it that's the center-seeking force. And in this case, it would be the force of friction. Okay, so that'd be how you draw a free body diagram on this car. So let's take it a step further. The maximum speed with which a 945 kilogram car makes a 180-degree turn is 10 meters per second. The radius of the circle through which the car is turning is 25 meters. Determine the force of friction and the coefficient of friction acting upon the car. Okay, first I'm going to do is I'm just going to write what I know about this car. Okay, so it has a mass of 945 kilograms. It has a velocity or speed of 10 meters per second. And the radius is 25 meters. Okay, we're looking for the force of friction, and we're looking for the coefficient of friction, also known as mu. Okay. So the first thing we probably would need to do is draw a free body diagram of this car. Okay, so I'm going to do that. All right, so we have the normal force, we have the force of gravity, and we have the force of friction. Okay, let's first figure out what the force of gravity is. Okay, and so remember, to figure out the force of gravity, I'm going to take m times g, mass times the acceleration due to gravity. So the mass of the thing is 945 kilograms times the acceleration due to gravity, which is 9.8. And if you do that math problem, I get a force of gravity of 9,621 newtons. Okay. Well, since there's no other forces in the downward direction, this force must be balanced out by the normal force. Okay, if it wasn't, then the car would be accelerating either up or down depending on what direction the net force was in the vertical direction. So my normal force must also be 9,621 newtons. 9,621 newtons. Okay, let me change pen colors here. Let's do green. So the net force must be from the force of friction, right? The force of friction must be the net force. And so we know this formula, F net equals mass times acceleration, right? Do I have the mass of this car? The answer is yes, I do. It's 945 kilograms, right? Do I have the acceleration? I don't, right? But I do have this velocity. And if you remember in the previous lesson, we said that the formula for acceleration is v squared over r. Okay. Do I have v? I do. Do I have r? I do. So basically I can plug this term in right here. Okay. I can just say m times v squared over r is the same thing as m times a. So I have 10 squared over r, which is 25. Okay. And basically if you do this math problem, you get a net force of 3,780 newtons. 3,780 newtons. Okay. Now that net force is actually the frictional force. Okay. That is the force of friction that's allowing this car to make this turn. Okay. So that's one thing I'm looking for, is the force of friction is 3,780 newtons. Now, what is the coefficient of friction? Well, if you remember, the formula for friction is force of friction equals mu times the normal force, right? F sub n. Well, if I just move the normal force over here, so I have mu, wish I could make my mu look better, mu equals the force of friction over the normal force. Okay? And basically, if you just plug in the force of friction, which is 3,780 newtons up on top, and the normal force, which is 9,621 newtons from my free body diagram, you would get a mu of 0.408. All right, 0.408. That would be my coefficient of friction, and this problem would be completed. All right. So roller coasters, don't know if any of you guys have ever ridden a roller coaster before, but roller coasters are all about changing your velocity, or the acceleration is changing. And that's actually what makes them very thrilling, is that, you know, you'll be turning left and right, going up and down, going through loops. And so it's not so much that you're going so extremely fast per se, but it's that you're constantly changing directions. I mean, really, you can make a 30-mile-per-hour car ride pretty fun if you were swerving and weaving and dodging all over the road, right? I mean, that would be pretty exciting. You know, you're going 30 miles per hour, it probably would feel pretty crazy if the driver really, you know, turned the steering wheel quickly and caused you to change your directions all the time. And that's kind of what a roller coaster does. Roller coasters also are able to cause feelings of weightlessness. I don't know if any of you guys have ever gone over a bump, and this sometimes happens actually if you go over like train tracks too fast with your car. You all of a sudden kind of fly to your seat, and for just a split second you feel lighter. Also, roller coasters will make you feel heavier. If you've ever been on a roller coaster and you have gone on one that has like a loop, you go through the loop, and as you go down to the bottom of the loop, you kind of get pushed down into your chair and you feel heavier than you really are. And it's not that your mass is changing, it's basically you're feeling the normal force changing, the force of the chair pushing on you changing, okay? And basically it's there to help balance out the force of gravity. Okay, so and basically roller coaster loops, they aren't actually perfect circles. If you ever look closely at one, they're referred to as a clothoid loop, and they actually changed this a long time ago. I don't know the date exactly in my head. Basically, because if you made it a perfect circle, the amount of speed at which you'd have to send a roller coaster through the loop so that it would actually make it through the loop was causing people to like have their bones broken and all sorts of nasty things happening because it was just so fast. And if you slow it down too much, the coaster wouldn't stay on the track, and that was causing people to like die. So that's not good either. So they've changed their shape of it basically to kind of help make it so that, you know, it's safer to ride and people still have a good time and they get to go home at night, not that they're dead. So that's a plus. Anywho, looking at the forces on a roller coaster, there actually aren't all that many because we will, for the most part, neglect friction and air resistance. So if we ignore friction and air resistance, a roller coaster will experience two forces: the force of gravity, which always points down, and the normal force, which is always perpendicular to the track. Okay, so it just depends on where you are in your car in terms of what direction the normal force points. And you can see here, like at the bottom of the loop, the normal force is very large based on how big this arrow is compared to the force of gravity. And the reason why is the normal force has to be stronger than the force of gravity, or else the car would go right through the track, and it has to keep you going in this loop. And so that's why you feel really heavy at the bottom of the loop. Whereas up here, you'll notice the normal force is actually very small compared to the force of gravity. And that's why you actually will sometimes feel weightless, like you kind of fly out of your chair for just a second. So the normal force is always perpendicular to the track. The force of gravity always points down. Keep that in mind as we start to do some roller coaster problems. For calculating gravity and the normal force, well, gravity, I'd hope by this point in time you'd be okay calculating gravity, but if you forgot, the force of gravity equals m times g, g being the acceleration due to gravity. The magnitude of the normal force, or the numerical value of the normal force, depends on three factors: the speed at which the car is traveling, the radius of the loop, and the mass of the rider plus the car. Okay, so the mass of the object going through it. So normal force is always kind of in a fight with gravity, and the normal force has to win to keep circular motion going. Okay, if you don't have a net force towards the center and gravity wins, you aren't going to keep going in that loop, and the car either falls off the loop or it crashes down through the center or whatever. Something bad happens. Okay, so you have to keep the normal force stronger than the force of gravity. So let's do an example of this. It says Jim is on a roller coaster. Jim experiences a downward acceleration of 15.6 meters per second squared at the top of the loop and an upward acceleration of 26.3 meters per second squared at the bottom of the loop. Use Newton's second law to determine the normal force acting upon Jim's 864 kilogram roller coaster car. Okay, great. I'm just going to draw a picture of this scenario. Okay, and here is a roller coaster as best I can. So we have two scenarios. We have one where Jim and his car is at the bottom of the loop, and one where Jim and his car is at the top of the loop. And this typically is the type of problems I'm going to ask you. It's either at the bottom or at the top of the loop. I probably will not ask you any questions where they're at the sides. Okay. So at the bottom of the loop, let's draw a free body diagram for this roller coaster. Let me just change pen colors here so that we can be more clear. At the bottom of the loop, the car experiences the force of gravity, and that's always down. And to balance the force of gravity, you have a normal force pointing up or perpendicular to the track. Okay. Whereas here at the top of the loop, you have the force of gravity pointing down, and you actually have the normal force pointing down. And the reason why is because it's perpendicular to the direction of the track. The track can't physically pull your car up, if you will, okay, unless it has hands or something crazy. So the normal force is always going to be perpendicular to the surface that it's on. Okay, great. I'm going to basically break this down into a chart where I have the bottom of the loop, and over here I will have the top. Okay, so let's deal with the bottom first. Okay, the bottom first. One of the things that I can do is I can probably calculate the net force on the bottom of the loop. Right? And the way I would do that is the net force has to be towards the center of the circle, right? So the normal force must be bigger than the force of gravity, okay? So let's first, before I do that, let's figure out the force of gravity on this object, okay? So the force of gravity is m times g, right? And the mass of this car is 864 kilograms times the force of acceleration due to gravity, which is 9.8. And so I get a F sub g of 8,467 newtons. Okay, so for this object to stay going in circular motion, the normal force must, at the bare minimum, be bigger than this number. Okay, it has to be bigger than that, or else the force of gravity wins and the car breaks through the track and off it goes. It falls to the ground. Okay, so the net force basically is going to be something along the lines of this: F net equals the normal force, because I know it's going to be bigger, so I put it first, minus the force of gravity, okay? So the normal force, I don't know what that is yet, right? And that's actually what I want to calculate, right? It says use Newton's second law to determine the normal force, okay? So what is F net? Well, F net is mass times acceleration, ma, right? So F net is ma equals the normal force minus the force of gravity. Well, can I get the normal force all by itself if I just manipulate this equation a little bit? I can. Let me just change pen colors one more time to make this a little bit more clear. F net equals, I'm going to add the force of gravity to both sides, F sub g plus m times a. Okay, cool. Well, what do I do? Well, I'm going to plug this number here into the force of gravity. The mass, it says that this car has a mass of 864 kilograms, and they give us even the acceleration. How nice of them. The acceleration at the bottom of the loop, at the top of the loop, and an upward acceleration of, 26.3 meters per second. So basically, I'm going to take 8,467 plus 864 times 26.3. Okay, and whatever that equals, that is my normal force at the bottom of the loop. And if you do that if you do that math, you would get 31,190 newtons. That is the normal force, okay? And notice how many times bigger the normal force is than the force of gravity, okay? You're really going to be experiencing a lot of G's, if you will, many times the force of gravity, okay? So you're going to feel really heavy at the bottom of this loop is the point. If this whole scenario was true, that the radius was this, the acceleration was this, and all that kind of stuff, okay? What about the top of the loop, okay? The top of the loop, basically, I want to figure out the force of gravity, which, unless the car's mass has changed, that someone like threw up before they got to the top here, it's still 864 kilograms, right? So I'm still going to use this number of 8,467 newtons. The force of gravity doesn't change just because it went through a loop. Okay, so man, I cannot write today. 8,467 newtons. I'm sorry, that's what that says. 8,467 newtons. Okay, that's the force of gravity. Now, how do I find out the normal force? Well, I'm going to be using a similar equation, but not the same. F net, the net force, must be pointed towards the center of this circle. What forces are pointed towards the center of the circle? Well, the normal force is, yes, and the force of gravity. So this time the force of gravity, if you will, is helping the normal force. So I can now write F sub n plus the force of gravity, because it's helping the scenario. It's not going the opposite direction. Okay, so notice in this equation, it was minus the force of gravity. In this equation, it's plus the force of gravity. Now, F net is m times a equals F sub n plus the force of gravity, which we now know is 8,467 newtons. Okay. So I'm just basically going to manipulate this equation around to get F sub n equals ma plus 8,467 newtons. And if you plug in the mass of the car, which is 864 kilograms, and if you plug in the acceleration, which this time is a little different, it says at the top of the loop it has deaccelerated. It's now 15.6 meters per second squared. So it isn't as quick as it was at the bottom. Okay, so if you plug those numbers in, you would get a normal force of 5,011 newtons. 5,011 newtons, a normal force of 5,011 newtons. And you'll notice here, it is quite a bit less than it was at the bottom of the loop. And the reason why is because now the force of gravity is aiding in continuing to keep this roller coaster car in circular motion. It's helping do that. So the magnitude of force on a roller coaster is really going to be looking at a couple things. The velocity and the radius affect the acceleration. And we can see that in this equation here, right? A equals v squared times r. And changes in acceleration are directly related to the amount of net force. So if you increase the velocity, the acceleration is going to increase. If you increase the radius, the acceleration is going to decrease. So try to look at these equations as ways of thinking, if you will. What happens if you do one thing to one variable? How does that affect the other side of the equation? Physics is a lot about that too. Not so much just always plugging numbers into equations, but just saying, well, if nothing changes about this roller coaster, but let's say I double the velocity. So if I double the velocity, I'm actually going to square it. So it's going to be 4 times the acceleration. The acceleration will be 4 times bigger by just doubling the velocity. Okay, so those types of things are really key to kind of even just checking your answers when you're doing problems. So as it says in the bottom here, a large speed results in a large acceleration, and that means a big net force, okay? A large radius results in a small acceleration, and so thus you have a smaller net force. This, beyond roller coasters, I don't know if you guys checked out the Olympics, especially the Winter Olympics, but if you watch an ice skater, when a person makes a turn, and in particular like in speed skating, on a horizontal surface, the person often leans into the turn. And you may say, why do they do that? Well, the leaning into the turn basically causes the surface, the ice, to push upward at an angle to the vertical, okay? So instead of just being straight up and down, you now have this angle here. And so that angle, there is a component of this force that is directed in the x direction. Okay, now if you guys remember when we broke vectors into components, there is now a component in the x direction that is helping this ice skater make that turn and continue to go in a circular motion. Okay, and so that's why they angle themselves. If they stand straight up and down, I think they'd have a really hard time going in a circle, especially at a quick speed. So the contact force plays two roles. It balances the downward force of gravity, so there definitely is a portion that is pointed down to balance the force of gravity, pointed up to balance the force of gravity, and it creates the centripetal force to basically allow the skater to continue turning. So it's kind of cool, at least I think anyway, that you can kind of see physics in real life and how these things actually are allowing us to do what we kind of take for granted in everyday life. That takes care of this video. I will see you guys next time.